we've basically introduced the fundamental ideas and fundamental concepts of this world of electricity. And you remember there are two sets of fundamental quantities, right? Some vector quantities and scalar quantities. So I will start from that. So vector quantities, you remember we introduced the electric force, then also electric field as the force divided by the value of the probe charge. And then at some point we decided to switch to the scalar quantities. Instead of force, we introduced the potential energy, electric potential energy. Both of these quantities describe interactions. So pretty much we're replacing quantity with a similar quantity. And we're not replacing apples with oranges, right? Then, instead of electric field, which describes electrical aura, we introduce the vector quantity, the electric potential. Again, they describe the same thing, but vector quantity and scalar quantity. Then, of course, fundamental formula how we can find electric force. If you have a charge exposed to some electric field, Q times E gives you force acting on the particle which is exposed to the electric field. Similar, if you have a particle exposed to, again, electrical aura and you know the value of the electric potential, charge times the value of the electric potential gives you potential energy. Right? Okay, then, so for particular systems, point charge and parallel plate capacitor, so all these things. So force for, of course, Coulomb's law, interactions between 2 point charges. Of course, we all know that, KQ, Q over R squared. Then, if you replace electric force with the potential energy, we derive it, and we got this formula. Potential energy of these interactions, so KQ small times Q capital divided by R, first power of R. Again, vector quantity, scalar quantity. And then, if you introduce electric potential, you just basically need to remove the value of the probe charge. You will get the electric potential at this point created by that point charge Q capital. It's a KQ capital divided by R. So, very important things. Of course, we're going to use it. Then, if you have now a system of a capacitor, which give us a uniform electric field, right? So, of course, if you want to find the force, let's say you position point charge in the inside of the capacitor, of course, force can be found Q times E. It's essentially the same. Then, if you make a transition to the potential energy, Q times the value, this is the value of the electric field, times X. X is a distance to the point charge from the negative electrode. You remember that in your quiz, recent quiz, you had to use that idea, right? And, of course, this part, E times X, it's essentially the electric potentials, right? So, if you take potential energy divided by the Q, potential energy divided by the Q, Q disappears, and you have the expression for the electric potential, right? So, we used it just recently. And then, also, we introduced an alternative way of finding electric field, Gauss's law, right? So, you can use this to find the electric field, or you can use Gauss's law. So, if you have some charges, you can pick any, literally any, closed surface, but it must be closed. So essentially, it's a closed surface, not some closed loop. And so if you calculate this integral, which is essentially flux, electric flux, through your chosen Gaussian surface. So that flux must be equal to the total amount of charge enclosed by that Gaussian surface divided by our universal constant epsilon naught. And Q enclosed, in this case, it's a charge 1, 2, and 3. Charge number 4 is outside. We're not counting any charges outside. Okay, so that is also definition of the electric flux. In the simplest possible case, E dot A. This is in general. This is special case. Okay, and the last piece which we need for this exam, properties of conductors in the electrostatic equilibrium. So we spent like 2 classes discussing that. So if you have a piece of metal, first of all, they have tons of free electrons. They're free to move anywhere they want, or you want. And we found, so if you are exposed to this piece of metal, no, if you dump some amount of charge or expose it to some external electric fields or something like this, right? So then electrons will move and distribute themselves in such a way to make electric field inside 0. Otherwise, electrons will never stop running, they will keep running and running and running to make net electric field inside 0. So then, if there are any excess charge on the conductor, that excess charge must reside on the external surface of this conductor. Right. Of course, distribution can be complicated, but that's another story. And then, since we also introduced the electric potential, we also just recently we proved that in the state of electrostatic equilibrium, electric potential inside of the conductor must be constant. Electric field 0, electric potential constant. Right? Okay, so that's basically the scope of first exam. So the first problem, very tedious. You remember, like at the very beginning, we added 2 or 3 vectors together. So let's just quickly do very similar steps. Right? Sorry, it's probably the most tedious problem in today's exam review session. So let me put number 1. It's a problem number 1. And so what do we have? You know what? I will start with a picture. And I will start with a coordinate system. Let me do it here. Let me estimate the amount of space that I might need. So this will be my y-axis. Then this will be my x. All right, so coordinate system. And 2 charges. One is negative, one is positive. So let me position negative charge over here. Oh, I will write down the value later. And positive, let's say here, plus. Right. So 2-point charges. Values, of course, I don't remember. Let me write it down. Q1, 10 nanocoulombs. This is my n, you remember, right? So n small, because it looks like U. And Q2 equals to minus 10 nanocoulombs. Essentially, it's a dipole system. And so these coordinates of this point, of this charge, x equals to 1. Of course, this is the origin. X equals 0. Right? So this charge, you see, is at the origin. And this is coordinate 1 meter. OK, so now, physical situation. These 2 charges create their own electric fields at every point, electrical auras. Right? So if you pick any point, of course, you need to ask about the net electric field. What will be the net electric field created by these 2 point charges? And of course, we can pick any point. Right? And this situation is quite common on the exams. I just create a configuration of 2-point charges and ask for the net electric field. It's a very common problem. So in this situation, I decided, what if I take this point, which is x equals 2 meters. Oh, not x, sorry, y. Y, this is the y-axis. Y equals 2 meters. So this is our point in question. Did I label it somehow? Yeah. Let me call it point, I don't know, point P. So we need to find the net electric field at that point. So we need to find E vector at point P. Right. Again, in the recitation, in the lecture, we solved similar situation, but we found what? We found the force. At this point number 3, there was actually charge. And we found the net force acting on that charge. But now there is nothing over there. Right? We just want to find the value of the field, right? Let aura. Right? Because very often still at this point, students not very comfortable, don't see the difference between the electric force and electric field. Sounds like almost the same. OK. So first, let's just complete the picture, draw all the vectors. So first, contribution to the net electric field from the negative charge and then from the positive charge. So contribution from the negative charge towards the negative charge. You remember electric field lines. OK, so let me draw it. So this will be, let me label it as E2. Right, E2. Then contribution to the net electric field from the positive charge. Let me draw a dashed line. Of course, will be away from the point, right? You remember, away. Electric field lines created by the positive charge, they go away. Right? So over here, it means that electric field will be this way. So it's a E1. Okay, and now we need to find the net electric field, so we need to add them first graphically. And guys, I was still kind of surprised that you don't have that strong habit of drawing parallelogram in order to add two vectors. Very often, like in the first year, remember first quiz, right? So you were drawing very, very distorted figures. No, you remember how to draw it. So you need to draw the line, for example, from this, which is parallel to the second vector. So draw dash line. Then from this point, you need to draw a line which is parallel to that vector. So you created a parallelogram. And you need to connect this, use that diagonal to get the net electric field in this case. So this will be the electric field, net electric field. But again, it must resemble parallelogram. Don't distort it too much. Right. Okay, that's it. So pretty much now we have everything in front of our eyes. We have a geometry. We have electrical part of the problem. And now, again, what's the strategy? Can we find the magnitude of this vector E2? Bree, can we find the magnitude of this vector E2? We have the formula for the electric field, right? KQ over R squared. Value of the charge is given, right? Distance, this distance is 2 meters. Given. So pretty much we have everything, so we can find the electric magnitude of this electric field E2. And then we can easily find components because we see the geometry, we see it on the picture. And then we can do the same. First find the magnitude of E1. Again, it's slightly more complicated, but still straightforward. And then introduce one of the angles. We should be able to find X and Y component of that vector. And then you have two vectors presented in the component form. You just need to add corresponding components and the end of the problem. Very tedious, I know. You just need to just go through that pain, right, smiling. All right. So yeah, we'll probably start below. And you know what? Let me start with more complicated E1. Let me first handle E1. So I will put a new bullet, and so first let's find the magnitude. E1 equals K. Absolute value of the charge Q1, although it's positive, so it doesn't matter absolute value or not. And divided by the distance from the first charge, square of the distance, to the point in question, right? Electric field, it's this, right? It's not a potential, so second power of R downstairs, right? Okay, so R1, it's at this distance from the charge to the point in question, R1. And of course, we know how to find that R1, right? I'm not even asking you. Pythagorean theorem, right? So it's a square of this distance, which is 1 meter, plus square of this distance, which is 2 meters. Yeah. So I will open my explanation box and write that R1 squared equals to 1 meter squared plus 2 meters squared. Right. So it will be okay, let me write R. So it will be square root of 5. Square root of 5 meters. Right, so that's R1. Okay, so charge is given, K is given. You see R, you plug, you crunch numbers, and you will end up with, I'm not going to do it. You will end up with 18. Units of the electric field, you remember?
Newtons per coulomb.
Yeah, newtons per coulomb. So there's no special units, just whatever you see in the formula. Newtons divided by coulombs, right? Soon we will introduce volts. We already introduced volts, and it also can be written as volts per meter, but essentially it's the same. Newtons per coulombs, volts per meters, you can connect them. But that will be soon in the future, in the near future, but not now. For now, newtons per meters. Oui. Volts per meters, newtons per coulomb, so my brain combined them together. All right, okay. So that's the, again, magnitude of this vector E1. So now we need to start finding components. And in order to find components, we need to introduce one of the angles. And you know what? In my notes, I decided to introduce this angle, use this angle, theta. You can use this angle, it will be as good, but whatever motives, I decided to pick that angle. All right, and so now, of course, we need to find components. So this will be our y component, E1y, and this will be our x component, E1x, right? X and y components. Okay, great. But of course, first we need to find the value of that angle. And of course, by geometry, you see that this angle and these angles are the same. Right, you see. It's the angle between this line and the horizontal direction. Right. So, and out of this triangle, we can find tangent of this angle. Of course, it will be opposite side versus adjacent side. Opposite 2 meters, adjacent 1 meter. Good, Pavlik? Again, I usually remember your last name because I told you it's easier for me. Sorry. All right, tangent of theta equals to opposite side. It's 2 meters divided by 1 meter. So of course theta, you can take arctangent, and of course you will end up with what? 63.43 degrees. I use more sig figs, right, just to be safe. Right. Okay, so now x and y components. E1, let me do x. So which function in order to find this side? It's an angle which we choose. It's adjacent to the side which we want to find. So it's, of course, it's a cosine function, right? So it will be E1 times cosine of that theta. Okay, and what do we have to add? Or maybe we don't have to add anything. Is everything okay with what I wrote? You remember that at the very beginning of the semester, we had that big discussion. I was asking about your feelings in the physics class. Look, you look confused. This is our vector E1. And we want to find this component. What's the direction of this component? You remember the discussion, right? You remember? Yes. Yes, so it's the negative x direction. So we need to, since we're not using conventional angle, we use convenient angle less than 90 degrees. So if you use convenient angle, so you have to take care of pluses and minuses manually. If you use conventional angle, which is from the positive x direction to that angle, to the vector in counterclockwise direction. So of course, in that case, pluses and minuses will pop up automatically. But since I don't like using angles larger than 90 degrees, right, and most of the people also, so you have to be careful. Look, and that's why you have to draw the picture, because it's supposed to help. It's like 30% of the problem is usually in the picture, right? Okay, minus manually, right? Okay, so now the value of E1 is given. Angle we have, so you can multiply and you will get, what did we get? It will be minus 8.05 newtons per coulomb. So that is the x component of the this electric field. And now we need to do similar with the y component. Of course, if we use cosine, now it must be sine. And so plus or minus now. Not still, now it's plus. Here we had minus to add, but now the y component is in the positive y direction, so it goes with plus. All right, so, right. Okay, so now you can plug again numbers, do the calculations, and you will end up with 16.09 newtons per coulomb. Again, just in case I keep more significant figures. Of course, on the exam, I usually don't care much about sig figs, but of course, if a problem gives you if the problem gives you numbers with, I don't know, 3 sig figs, don't give me 10 sig figs at the end your answer, because that would be slightly bizarre. Right, okay, so we solved 30% of the problem, so we found components. Now we need to do the same with E2, but that is obviously much, much easier, right? So let's do the same with E2. All right, let me separate it, and I will put a new bullet. So now magnitude of E2, it's a K Absolute value of Q2 divided by R2 squared. Why do I put an absolute value sign? Now it's you have to put. No, not exactly, not exactly. What's the value of the charge? Negative. If I don't put a sign of an absolute value, what I'm going to get? But we're finding what? We're finding the magnitude of the vector. You remember I kept already several times mentioned in the semester, magnitude of any vector cannot be negative by definition. It's a sort of like a length for the distance or displacement, but in this case, overall, in general, it's a magnitude. Magnitude cannot be negative, and I see every semester, maybe like 15% of students find negative magnitudes, right? So no, you have to develop a strong habit, right? So essentially, we're combining. We find magnitudes of the vectors, and then by looking at the picture, we make the decision: is it positive or negative, and so on, by doing all that. Right? So that's why I put an absolute value, because we finding the magnitude. So, and even let me write, it's a magnitude. So that's why we have that absolute value sign. Okay, R2, value of R2. Now it's from the charge to the point in question. So that is R2, which is 2 meters. You see, from the picture, you can see it immediately. So R2 equals to 2 meters, right? Okay, so charge is given. K, of course, you know. If you crunch numbers, you will, but of course, don't forget to square, because again, maybe like a few % of students make that silly mistake. Just be careful, right? So you will end up with what? 22.5. 22.5 newtons per coulombs. Right. Okay, so now, of course, we don't need any angles. We can write immediately x and y component, right? So E2x and E2y. So E2x, what's the value of x component of the electric field? 0. Yeah, because it's on the picture. That's why I keep saying we need to see the picture in front of our eyes, because it will help immediately. So x component obviously 0, so the whole vector is in the y direction, right? So 0, and all this will be in the y direction. And is it positive or negative? Negative, because you see the vector is in the negative y direction. So this component, y component, will be negative. So it's minus 22.5 newtons per coulombs. Okay, so now we have the second vector written in component form. All right, so let me check. Yeah. And so now the final step, we just need to add these two vectors to find the components of the second vector. I mean, of the net vector. So next bullet. So E equals to E1. Of course, E, it's a net electric field. E1 plus E2, right? So it means that we need to find, we need to add corresponding components. X component, and then the same with the y components. X components, this is 0, great. So it's just everything comes from here. Negative 8.05 newtons per coulombs, right? And y, we need to do some calculations. Y equals to E1y plus E2y. 1609 minus 805. No, I will use my notes. Minus 6.4. Make sense? Yeah. So it will be minus 6.4 newtons per coulombs. So, and it sort of makes sense. You see, our net vector is somewhat point this way down. So it means that y component will be negative, right? And x component also negative of this vector E1. You see, because it's it's in the third quarter essentially. So where x and y components are negative, and we got negative and negative, so it makes sense.
Right? Of course, it's out of scale, this picture, but I tried to keep it somewhat in scale. So, done. Right. Again, it's a very tedious, ideologically very straightforward. You just need to be careful, right, with pluses, minuses, which angle you use, and so on. Right? Yeah. And almost every exam I give something like this. It can be about force, it can be about electric field, but ideology exactly the same, because you remember, vector algebra, it doesn't care what's the nature of that vector. It just wants to know, are you a vector? Yes, okay, then I will treat you as a vector. Right? But what's the nature? Is it electric field, electric force, acceleration, displacement? It doesn't matter. Mathematics doesn't care about that. Right? So procedures exactly the same. Okay, good? Okay, great. So let me get some water. And so now let's answer a few conceptual questions. And why is it blinking from time to time? All right, so let me label it as, for example, 2-1. So this is done, so let's say 2-1. That was problem 1, and now problem number 2, and since it's conceptual, I decided to divide it into several by using the second digit. Okay. Let's assume this. We have 2 point charges. One is positive plus q, and one is negative. Yeah, minus q. You know what? I don't like it's too close. Minus q. Essentially like what we have over here. But now I just want to add vectors graphically, just to practice that, because as I noticed, again, you have problems with parallelograms. So what if I pick, for example, we discussed this point. Let me pick what? Maybe over here, this point. Right. So let's find just find the net electric field at this point. No numbers, nothing. So electric field, a contribution to the net electric field from the negative charge towards the charge, right? You remember towards, because electric field lines, okay, you look confused. So if you have a negative charge, electric field lines will be like that, right? So essentially negative charge, and our point is essentially somewhere over here. So of course we'll repeat it that way. So this will be contribution from this negative charge. Then contribution from the positive charge, let me use different color, away from the charge, yeah, so it will be this way. And now we just need to add them again properly. You just need to complete a parallelogram. Remember that all the time. So first draw a line parallel, oh, it's not very parallel. Parallel to the second vector. And from this end, draw the line parallel to that one. Okay, more or less decent. And now, so the net electric field will be this way. So E. Okay, sort of similar to that, but now we picked a different point. Okay, I think it should be enough, right? Yeah. Because again, I was surprised when I saw the parallelograms in our first quiz, so I decided that I need to emphasize on that. Great, so now let's say a few words about the force, electric force. Let me say it, this is 2.2. Let me separate it first. And now the question 2.2. So let's imagine that we have this sort of like a pendulum. What if we have this ceiling, and here I have a charged particle, let's say positively charged, yeah. Positively charged, let's say Q, right. So displaced, of course there's a gravitational field, right, so acceleration due to gravity, but the pendulum is displaced that way because of the presence of some electric field. Let's assume uniform electric field. But I don't know the direction. By looking at this picture, can we say what's the direction of the electric field? Are the electric field lines pointing this way or that way? To the right or to the left? Okay, not sure. Let's first imagine, so which forces are involved in this situation? Of course, there will be force of gravity, ubiquitous, right? mg. Physics 1, you remember. Then, there is a cord attached to the charge. There will be, of course, tension along the cord away from the object. Tension. And since this charge is displaced and it's not moving, so it means what happens with the net force? They all balance each other out. The net force must be 0 in all directions, in x and y direction. In order to balance this force and that force, what should be the direction of the electric force acting on the charge? Of course, that way. Because if the force that way, system will never be stationary. It will just move that way, right? So, of course, the electric force must be this way. So, Fe must be this way, okay, in that direction, in order to have a stable system. And now you see the direction of the electric force. And so now from this, you should be able to tell what's the direction of the electric field. You don't need, over there is nothing. Look. You remember this fundamental formula for the electric force? So since charges, so now we see the direction of the electric force. Do we know, do we have information about the charge? It's positive. So it means the direction of the electric field and the electric force must be the same, right? Must be the same. So it means that electric field lines must point this way, right? So it's not that bad, right? So once you put everything together, right? Again, but if the charge was negative, of course, electric field should have been that way, right? Only in that case, the system would be stable, right? Okay. So I just wanted to practice that formula for the force. F equals Q. Yeah, it's a physics 1. Yeah, we have some problems where it's a good mix of physics 1 and physics 2. Just the nature of some forces are electrical. That's the only difference, right? So we see this, and since the charge is positive, so we can say that E is in the direction of F, in the direction of the force, F electric force. Just from the formula, everything comes. Okay, great. Now, another conceptual question. Also reasonably straightforward. 2.3, but you just need to develop a habit of analyzing these formulas. An analysis, you see, it's trivial, nothing complicated. So now let's imagine this situation. We have uniform electric field lines. I used to discuss it in the recitation classes, but for the last couple of years I stopped. Let's assume that we have these electric field lines, E. And let's shoot an electron. So let's shoot an electron this way. So it's a E minus, so essentially it's a charged electron. And it flies with velocity v naught that way. Maybe I'll draw another electric field line. Right, so uniform electric field lines, electric field we assume. So now let me offer you a few trajectories. So possible trajectory. This way, which way I label it? Let me start with this. And you know what, let me use blue. So first option, let me use green. Right. So trajectory A, is it possible or not? Trajectory B, is it possible? Wait, force of habit, sorry. Trajectory C, or this trajectory D. So which trajectory is possible? Electron, we shoot inside of the electric field. So which trajectory is possible? You understand now, it's about the same formula, F equals QE, right? D? Yeah, D, of course, right? So again, it's all about that formula, fundamental formula. QE. So since our charge is negative, and we see electric field is up, electric field line, so it means that force will be down, right? So of course, for an electron, for that electron, trajectory D. Okay, now let's imagine you're an experimentalist. It's your experimental setup. You can do anything you want with this setup. You have all the possible charges. You can replace electron with proton, neutron, whatever. Then you can turn off this electric field. You can change the direction. You can do whatever you feel like doing. So what do you have to change in this setup in order to get, for example, trajectory B? First, you can flip the direction of the electric field. Right? So one choice. Then what else can be done? You have a bunch of particles in your box, right? So you can pick any particle you want. You can change electron, for example, with the proton, with a proton. So in that case, of course, the force, without changing the direction of the electric field. So of course, it will follow along that trajectory, right? Then what do you have to do in order to get trajectory C? You still have neutrons. We have a reactor, we have a nuclear reactor, tons of neutrons. They generate them non-stop, essentially, right?
Not here.
Not here, but you know that dome, white dome, that's a nuclear reactor.
Oh, yeah.
Yeah, so it's
Yeah,
a...
one of my friends works there.
So yeah, you can either turn off electric field, and any particle will fly this way, or use the neutrons. They will follow trajectory C, right? So what do we have to do in order to get trajectory A? That was usually the most complicated in the classes. Still, you can do anything you want with those particles. Trajectory A.
I guess change the field and stop it.
V naught. What if you just...
Oh, is it zero?
Yeah, if velocity will be zero, only in that, if velocity is zero, only then electron will follow, of course, down, but the proton will go up, right? So only if you turn off velocity, all right, if you release the charged particle, of course, it will follow either up or down, depending on if you have a proton or electron in the setup. Okay, so again, it's just I wanted to massage this formula for different situations. Great, so enough of these conceptual questions. Now let's solve one problem about the electric force. I've been using this formula, this problem for a few years in the exam review session. Right, so let me separate. Right, and so this will be problem number 3. So let's assume that we have two charges. Let me draw first a line. And the first charge is here. Let's say it's a 4Q. Then there is a charge over here. Let's say just Q. Both of them positive. Let's assume positive and positive. Right. Along that line. And now there is a charge number 3. And then there is the third charge. Also plus Q. So we need to find the spot for this charge on this line only. We're not moving away from this line. So we need to find the spot on this line where the net electric force acting on the charge will be 0, where it will be just peacefully sitting. So we need to find a spot for this Q where the net force will be 0. So where it will be just sitting peacefully without being able to move anywhere. Right. Okay, so let's first, there are 3 regions, region 1, region 2, region 3. Let's just discuss where it's just physically possible. And then we will just dive into that region and analyze and find actually that spot. Okay, so let's imagine that what if this charge position over here, Q, let me use green. So is it possible to have net electric force acting on this charge 0 when it's here? You just need to draw vectors. So what will be the force that this charge, which this charge exerts on that one? And again, we assume that these two charges we nailed them; they cannot move.
5Q.
No. Look, I'm not asking about the value. I just want to see the direction. I just want to see philosophically, is it possible in this region to have net zero net electric? You think it's possible? Okay, let's draw then with you. I'm switching. Okay, this is positive. This is also positive, right? Let me even emphasize plus. So what's the direction of the electric force? Repelled.
Yeah.
Repelled. You showed that way? No. It will be this way. Force, no, hold it.
Force.
Question, force on which charge? Because right now you said force on this. Yes, there will be force that this charge exerts on that one, but we're not interested in that force. We assume that this charge is nailed, right? So maybe there are some forces acting, but just it cannot move. It cannot move. So force acting on this charge, that way. It's a force of repulsion. So this will be which way label it, F1 or what? Yeah, let me label it. It's a charge number 1, and let's say this is charge number 2. So this is the force F1. Then, what's the force that this charge exerts on that green charge?
The same direction.
The same direction, the same direction. Of course, it will be a different value, but so F2. So of course, both forces are in the same direction, so cancellation is not possible. So we can just exclude that region. So we can say that over here, in this region.
You could put it in negative infinity.
No, that's in the limits, yeah.
You didn't say there was upper limits to where we could put it. You could put it in any.
Okay, you got me. No, it's net force is not 0. Okay, so we can forget about this region, so it's out of the region. Then let's position, imagine that charge, green charge, is over here. So plus Q. So essentially we're going to see something similar. Again, F1 will be that way, and F2 will be also in the same direction. Again, the cancellation is not possible. So okay, sum of the forces is not 0 again, so we can cancel this. So it means that there is only one candidate over here, can be somewhere. So let me position charge Q here. Another piece of information is given. I forgot. This distance between these 2 point charges is given, L. Just now I realized that something is missing. Right. So that L is given. So, and now let's start thinking. So this charge is going to repel that one, so force that one, that way. So this will be force F1, this is 1. And this charge will repel that one, F2. So directions are opposite, so cancellation is possible. So theoretically it's possible. So now we just need to write some equation in order to actually find that sweet spot where the net force will be equal to 0. Right? Okay. So there, yes, it's possible. Yes, possible. Right. Okay. So and what we want to get this. So it means that this F1 must be equal to F2. F1 equals to F2. And again, it's this region. Right, this region. And so let's first introduce the unknown parameter. We need to find the distance. So let's introduce this distance as x between the charge number 1 and the charge number 3, right? So let's introduce that as x. And of course, then what will be this distance? L minus x, right, of course. The whole distance is L, so this will be L minus x. Okay, so now we can write F1 and F2. Right. So F1, it's this, so it will be K, for Q times Q, right? Divided by x squared equals to K. Q and that in this Q, so Q and Q, divided by L minus x squared, because the distance L minus x squared. Right. Did I introduce this? Yeah, that is x, that is L minus x, yeah. So there will be plenty of cancellations. K can be cancelled, Q squared and Q squared can be cancelled, right? So as a result, we're getting nice, simple, reasonably simple equation. 4 over x squared equals to 1 over L minus x squared. Right. Okay, so one unknown, one equation, physics is over, now we just need to solve it for x. All right, so I'm going to take a square root of both sides, right? I think it's logical, sounds. So I will get 2 over x equals to 1 over L minus x. So proportion, just multiply 2L minus x equals to x. Right, so in the final step, so it will be 2L minus 2x equals x. So it will be 3x equals to 2L. 3x equals to 2L, and from here we can get x equals to 2 over 3, 2/3 of L. So you need to position the charge 1/3 of a distance from the second charge, and at that point the forces are going to balance each other out, so that the charge will be in peace at that sweet spot. And let me check it. Yeah, I think it's correct. Yeah, it sounds correct. Okay, so far so good, right? So we played with this, right? And now let me play with the electric flux, Gauss's law, and then this energy approach. And then properties of conductors. I think now let's discuss properties of conductors. Yeah. So again, if something is not clear, let me know immediately, right? So that will be problem number 4. Yeah. I created a complicated conductor of a complicated shape. Let me try to draw it. So, conductor. So that's my conductor, right? So that it's charged. Conductor Q total amount of charge is it's negatively charged, minus 6 volts. Then inside of the conductor there are 2 cavities, something like this, and then second cavity will be here somewhere, 2 cavities. So this is our conducting material. So we solve problems like this. Again, it's a review. We're not solving something new, something fancy. No, we're just reviewing what we've got. And again, on the exams, I keep telling, don't expect something unusual, crazy, similar to what we have in the class. So now of course you understand, and I'm going to drop some charges. Let's assume that over here in this triangle, there is a minus 2 Coulomb charge, and then at this cavity, I'm going to have 2 charges, minus 3 and 8. Next time I need to find yellow marker and create additional charge, almost like a traffic. No, it must be green. Actually, I can fix it. It will be green. Okay. So, and you understand, you know what will be the question, right? Questions
First, let's answer the question, what will be the total amount of charge on this Q inner surface number 1? And then, of course, over here, Q inner surface number 2. So what is the amount of charge on the inner surface number 1? Of course, yeah, plus 2. So positive charges will be induced on this inner surface. And again, you need to understand that positive charges do not move. It doesn't mean that positive charges run to this surface. No, it's just electrons run away. The electrons see this negative charge, they run away further to the outer surface, or maybe to this surface, who knows, right? And leaving behind positive charges, which are essentially nuclear, right? So over here, there will be positive charges because electrons just run away. Distribution of these charges can be really complicated, but we know that the total amount of those charges will be equal to plus 2 coulombs. Again, how to prove it? Of course, you can use Gauss's law, but I usually don't ask. I usually don't ask that. If you just write down the correct answer, I'll buy it. It's obvious. Then, amount of charge on the inner surface number 2, just add them up, right? 8 minus 3, it will be 5, so negative 5 will be induced on that inner surface. Again, distribution will be complicated here, maybe more negative there, more positive, right? Distribution will be complicated, but I can bet all my money that the total amount of charge will be, just a second, minus 5 coulombs. So minus. So QI2, it's minus 5 coulombs. Again, it's a Gauss's law. And of course, you know now the question, what is the total amount of charge on the outer surface? There's only one outer surface, right? So now see what's the Q on the outer surface. It's like what we had on the quiz. And again, guys, be careful when you move charges from side to side. Right? So change the sign and then make sure that you include the fact that of this charge is negative. Because it's a really silly mistake, and you shouldn't be making those mistakes. Again, conservation of charge inside of the conducting material. This charge and this and that charge not part of the conducting material. Right? So conservation of charge inside our conducting material. Okay, deconducting our conducting material. Okay, so it's like I compare it to the 3-room situation. The total number of people is given, minus 6, and these people can be either on the outer surface, on this inner surface, and that inner surface. We just need to add them up and see what we're going to get on the outer surface. So Q total equals to QI1 plus QI2 and plus Q out. So we have this, we have this, we have this. We just need to find them. And now, once you get the idea, it's a banal problem. So from here, Q out. Great. Is everything fine? Good. Again, if something is not clear, tell me, because we discussed this in our recitation classes. So, and you see even I drew it carefully. So just Q total minus QI1 minus QI2. Even I remember once I made a mistake in my solution for this stuff. Right. So Q out equals Q total is minus 6 coulombs. Then minus from the formula and the charge, again, this is positive, plus 2 coulombs. Then again, minus from the formula and this charge is negative. So it's a minus 5 coulombs. Again, in the places like this and this, that's where most of the mistakes are. So let's calculate. So it's a minus 8 and plus 5. It's a negative 3, right? Negative, right? Yeah, negative 3. Yeah, negative 3. So it's a
minus 3 coulombs. Again, very common problem on the first midterm exam. Usually among multiple choice questions. Because again, it doesn't require much of the time and effort. But again, if you don't show your work, if you just show the answer, then if the answer is wrong, you will just get immediately 0. But if I see that the logic is correct and you made some silly mistake somewhere in the algebra, of course I will give you some points, right? More than 50% definitely. But if it's just an answer, it's either right or wrong. And so, what can you say about the electric field inside of the conductor? 0. Okay, now you. And it doesn't matter what's the distribution of charges outside or inside. Of course, it will make distribution of electrons complicated, but we can guarantee that the electric field inside is 0. Again, if you wait until it reaches electrostatic equilibrium, so it's a negative. Over here, I can draw a bunch of minuses. So it's a negative. Okay, now I think it's everything is on the picture. And of course, electric field lines, I mean electric field outside of the conductor is perpendicular, but you will see it in your lab number 2. Okay, enough of this. Now let's play with the electric flux. Because again, in your quiz number, the last one, there were some troubles. Because it takes time for you in your head to separate things. It's a field, this is force, this is flux, this is electric, and then you start feeling dizzy. So you know what, I will continue over here. I think I should still be able to fit into the camera. So now this will be question 5. 5.1 conceptual questions. So about flux, electric flux. So what if we have this situation? I have a point charge. Let's assume it's positive plus Q. And let me pick a completely out of the blue surface, this cylinder. Right, some imaginary cylinder. So it's surface, closed surface, right? And if I ask you, what's the total flux, electric flux, through this surface? Here. Here? No? Not sure. Not sure. Okay, in this case, so there are 2 ways of finding electric flux. So, first, direct way, by using the definition. But probably it's possible, but it will be ridiculously complicated in order to get that answer using the definition. Right? You need to integrate through each surface, and but there is an indirect way of estimating the electric flux. What is the Gauss' law? On the left-hand side of the Gauss' law. This. It's a flux. So this is and that flux equals to the total amount of charge inside divided by epsilon naught. So it's an indirect way of calculating or estimating the electric flux. So this is by definition direct. So that's how we define the electric flux, and that's too complicated. But this is the fundamental law which Gauss somehow managed to see and write it down, right? So, and it works. Right? We know it's fundamental. No one has found any examples where it failed to work. So since it works all the time, so we can see flux equals to Q enclosed over epsilon naught. So now what can you say about Q enclosed in that case? It's a total charge which is physically inside of your chosen closed surface. Our cylinder, inside of the cylinder, there is nothing. So the charge is outside. Who cares what is outside, right? The outside of the border. Right? So Gauss's law cares only about charges which are inside of whatever closed surface you pick. I pick that surface. That's my Gaussian surface, essentially, right? So
there is a inside there are no any charges, so the net total flux through this surface will be 0. It's the easiest way of estimating the flux. But if I put this charge inside, what? Move that cylinder higher to embrace that point charge, then of course flux will not be 0. Again, what does it mean, the 0 flux? It means the total amount of electric field lines entering the surface and leaving the surface, they're the same. But entering, they give us negative flux, exiting, they give us positive flux. So total number will be 0. It's like over here, I can draw, it's a positive charge, so electric field lines will be like this, right? And the total number of electric field lines entering and leaving is just 0. Right? So again, if the question is about electric flux, then application of the Gauss's law is trivial. You just need to look at the total amount of charges and divide it by the constant epsilon, the universal constant, right? Which describes electrical properties of the vacuum, and this is the vacuum situation. Okay, indirect way and through the Gauss's law. Okay, you know what? Yeah, E dot dA, which is the electric flux, equals to Q enclosed over epsilon naught. Since this is 0, electric flux is 0. On the Gauss's law, indirect way through the Gauss's law. Now, what if I create this situation? So let me separate it, and still the same, my cylinder. Right, so that's my Gaussian surface. Okay, closed surface, but I can use any closed surface of the Gaussian surface. And now, what if I create this configuration of charges? So over here I have plus Q, then over here minus Q, and then another charge where I drop it. Okay, another positive charge, for example, over here, plus Q. And now the same question. What's the net flux through that cylinder, through that Gaussian surface? Right? So now, of course, you can answer 0. It's 0. Again, this charge, who cares? It's a similar situation, right? So it just gives us total amount of positive flux and negative flux overall will be 0. But in these guys, yeah, this gives us flux positive. These guys give us the same amount of negative. Oh, yeah, negative flux. No, this will be positive flux. That will be negative flux. And now, if you add them up, you will end up with 0. But again, mathematically, just a Gauss's law. Q enclosed 0, the flux will be 0. So flux, again, total. So equals to Q enclosed over epsilon naught. So which is essentially plus Q minus Q over epsilon naught will be 0. So then, now let's make situation slightly more complicated. You know, let me check if I still fiddle. In the field of view. Yeah, I need to start erasing that. So that's yeah, it's pleasant to write on this whiteboard. It's kind of smooth, everything about in terms of reflections. So next, what if again my that cylinder? So that was, let's say 5.1. This will be 5.2. Question 5.2. And actually, this question is from one of the exams in recent past. A few years ago, I gave a question like this. So imagine this situation. So we have again cylinder, which I use for the Gaussian surface. So top, cylindrical wall, this is the bottom. And now let me drop a few charges. Over here, 5Q. This is again, every time it reminds me something when I draw this picture.
So like I had two openings, two holes and cylindrical. Yes, you got it right. So every time we have strong association from them. Okay. I'm not telling you exactly what are the associations. And then plus two coulomb charges, a charge outside. Then additional pieces of information. Let's say you somehow measured or calculated the flux, maybe let's say using definition, and you know that flux through this is top surface, this is bottom, and this is cylindrical wall. Let me label them like this. Cylinder consists of three surfaces, top, bottom, and cylindrical wall. So let's say I know that flux through the top surface somehow measured, calculated, it's a minus 15. There are no special units, so just whatever you see in the formula, it's a E times the newtons per coulomb times meter squared. Newtons per coulomb times meter squared. So this is given. Then we also know the flux through that cylindrical wall, which is 10 newtons times meter squared over coulombs. And so now, having this situation, we should be able to find what will be the flux through the bottom. So now it's slightly more complicated. It's not just this, but although this will be directly involved, is directly involved in that in this manipulation, right? Flux. Yeah.
Positive I. If the net enclosed is 0.
Okay, so first, flux is an additive thing. So what do I mean by additive? If I introduce the total flux through the whole cylinder, of course, that flux can be divided into three parts. Flux through the top, flux through the bottom, and flux through the cylindrical wall. Let's start with that step first. Right, you agree? Flux is an additive. We can divide it into as many parts as we want. And this we have unique surface of this type, this type, this type. Okay, let me write this. So flux total equals to the flux through the top plus flux through the bottom plus flux through that wall. Everyone agrees on that, right? Now, what can you say about the total flux? And of course, you see, this is given, top, and the wall is given. Can we find the total flux through the total surface? That will be what? 0. Is he correct? It's that discussion. That's why I prepared you for this problem with those two questions, right? So the total flux we can calculate using Gauss's law. So we're mixing stuff now. All right, so flux total equals to Q enclosed over epsilon naught, and of course, let me remind you, this we basically use Gauss's law. And Q is closed is plus 5 minus 5. That charge outside, I just put it there for fun because it doesn't change any. It's not a game changer. So 5 coulombs plus minus 5 coulombs divided by epsilon naught will be 0. So as a result, we calculated this. It was given. It is given, and it is given. And this is our question. One equation, one unknown, right? You see. So now, based on this. So now from here we can get flux to the bottom will be equal to total. And again, I will be careful when you move terms around because it's also place for unnecessary mistakes. So now I need to subtract the top and subtract the wall. Right, so it's a bottom, 2, 2, 2, yeah. So this is 0. Right. And this is top minus minus, minus minus 15. Right. 2 minuses. And again, minus from the formula, and the value of the flux, this is positive. So minus 10 newtons times meters squared over coulombs. So it's a 25 minus 10, it will be 15 those units. So the flux to the bottom will be, why did I say 25? Sorry, it's a 15 minus 10, it will be 5.
Yeah.
So 5 newtons times meters squared divided by coulombs. So, and the extension. So now we mix Gauss's law with dividing the surface into several parts. Okay, good. Great. Okay, it's already getting close to 1.5 hours. Gauss's law. Let me just quickly go through that problem. But of course, will not be as thorough as we did in the class because we already discussed similar problems. So let me start erasing this. So I guess for the Gauss's law, I need more space. It's a space-consuming problem usually. And the record amount of time for the exam review session, it was for the final exam before the lockdown, plus 4.5 hours. We have an exam review session from 5 till but that was the record. Again, we're not forcing, right? So yeah, it's difficult on me because after that I'm completely drained. I just go home and collapse. Right, so that was 5, now 6. Good. 6. So, non-conducting sphere with the hole, concentric hole. Okay, so not conducting, so it means that all these properties were not applying. Still, very often students do that. They try to apply them. So read the problem. If it's a conductor, yeah, grab that and start using it. If it's a non-conducting material, of course, do something else. Non-conducting charged sphere, change marker soon, with a concentric hole. Okay, let me draw. It's enough. No, I can do better. Even for Friday evening, I can do better than this. Still distorted. Good. So radius B, then hole radius A. Right. So non-conducting material is this. You know what? I will just draw a bunch of charges. I don't want to draw this highlight. Okay, good enough. So plus. So uniform charge distributed uniformly. Right? And the total charge is given. So, all right. So Q, it's a total charge. And let's add additional charge at the center. Let's say it's a Q small. So Q capital is uniformly distributed over that non-conducting material, and at the very center of this hole there is a Q small. Let's assume they're all positive. Okay, so Of course, I can ask questions about finding the net electric field at any region inside of this or outside. This example, let me pick the most complicated. Let's find the electric field in the material between A and B. So let's find, and then of course we will quickly conceptually discuss what will be the difference if we look at this region or that region. So find electric field when R is larger or equal than A and smaller equal than B. Again, we can use either this and integrate, but that will be a nasty integration. No, I would never recommend that. It's because we have nice symmetrical distribution of charges, complicated, but still nice and symmetrical. So Gauss's law is the law to use, right? So it's a pleasant application of the Gauss's law. And since the question is of finding electric field over here, of course, the Gaussian surface must be there. Of course, you can use any surface you so desire. I will never be able to tell that you are wrong, but you need to pick the most convenient, the most pleasant surface so that we can use the symmetry of the problem. And of course, the most convenient surface is another cylinder. I used too many cylinders. Is another sphere concentric with this sphere. Okay, so that will be my Gaussian surface. All right, of radius R small, it's a variable. So that's my Gaussian surface. And of course, we're going to use Gauss's law, so let me just quickly rewrite it. E dot dA equals to Q enclosed over epsilon naught. Enter the Gaussian surface. It's that one. Okay. So now let's, so we made all the preliminary steps. Now let's start evaluating the integral, like we did in the class. So integral of E dot dA equals. Okay, let me show I can electric field and the vector and the area vector. If you pick this part, this patch on the Gaussian surface, of course, electric field. You remember, by the convention, it must point towards the outside for the closed surfaces. That's convention, which is imposed everywhere. So this will be dA, all right, or if you pick here, it will be the same, dA, or here, dA. Electric field vector, of course, radially outward, right? So of course, I will not ask you for justification, but you at this point, you should be able to have a feeling. Right? And of course, in the class, I justified that electric field everywhere is radial. Now, of course, I don't want to justify it. It will be too much time. All right, so now we have everything in front of our eyes, and now let's start simplifying this integral because it's calculus 3 and this integral stuff are doing trivial. But we can simplify it and then use high school knowledge. So electric field is in the same direction of the area vector, so it means that dot product gives us a product of magnitudes because the angle between those two vectors is 0. A and dA, E and dA parallel, it means the angle between them is 0 cosine of 0 degrees is 0. Oh, it's 1, sorry. Right, so it's the integral of the Gaussian surface, E, dA. Again, achievement, advantage, what's the achievement? Here we have the vectors, now we have magnitude. So now we don't care about their direction. And now, again, we can use the symmetry. It doesn't matter on which part of the Gaussian surface you are, electric field magnitude is the same. Not vector, because electric field over here has that direction, electric field over here has this direction. Directions are absolutely different. Right? You see, directions are different, but since now we have magnitude, so but magnitude are the same. It doesn't matter where you are on the Gaussian surface. Magnitude stays the same. It doesn't mean that the electric field is uniform. No, it's just the electric field is constant on our nice Gaussian surface. Right? But of course, if you step away, for example, over here, electric field will be smaller. If you move closer, electric field will be larger. Right? So electric field is not uniform. So now I can open my another explanation box and I can write, since electric field is constant on the Gaussian surface, So I can extract any constant from the side of integration easily. Right? Any constant factor, not constant, any constant factor can be extracted. So I can write it equal to electric field times integral over the Gaussian surface, dA. And of course, the value of this integral, of course, we all know, although it's still plenty of integration according to the rules of calculus 3, but we know the answer. It's just the area of our Gaussian surface. 4 pi r squared. Again, formulas for the circumference, for the areas, for the volumes are given in the formula sheet, so just don't make those absolutely unnecessary mistakes, and still it happens quite often. So it's a 4 pi r small squared. E times 4 pi r squared. So that's the value of the electric flux through the Gaussian surface. And according to the Gauss's law, it must be equal to Q enclosed over epsilon naught. And now the fun part, Q enclosed, that's where students make a significant number of mistakes. Usually 30% of students only can go through that part. So now, Q enclosed. Yeah. Usually lots of mistakes, right? Yeah. It's getting better, it's improving, and because now we emphasize more and more punching, more and more with these examples, it's getting better, but still. Okay, so you remember I told you, it's all about this formula. Definition of charge density, nothing else. Again, it's a definition. Let me frame it. You can take any charge you want. It doesn't mean that this only. You can take any charge you want, divided by the corresponding volume over which that particular charge is distributed. You can use any charge, but you need to divide every time by the proper volume. So now, if I use this definition, and I want to apply it twice, for the total charge and for our Q enclosed. Where is our Q enclosed? It's essentially over here. That's my... Yeah, this charge. Of course, that charge will be also included, but I will include it later. Right? So I just want to find this amount of charge. This. And you know what? I probably should have labeled it somehow, that amount of charge. Because, why I stopped? Because this is in part of Q enclosed. So let me label this charge as, for example, I don't know, Q prime. Because this Q prime plus this, they will give us the Q enclosed. Right? So let me call this amount of charge as Q prime. Right? We want to find it. Okay, so I can write rho equals. First, let me use the total charge, Q. And we need to divide it by which volume?
The volume.
Can you tell me, in terms of volume of the sphere with radius this?
Oh, yeah, so there's a void, so we need to consider that in our volume. So it's some larger sphere minus the volume missing.
Yes, we need to subtract the whole. So we need to take volume of the sphere with radius B and subtract the volume of the sphere with radius A. So I can usually write it like this using subscript. So VB minus VA. Or you can use whatever annotations you want. So it's a total amount of charge I use because that is distributed over this sphere with the hole. So I use this. Now let me apply exactly the same formula, but now it's a for Q prime. Why not? So Q prime divided by, now we need to again do similar. Now it's a which volumes we need to use over here?
There's our pi,
Okay.
pi b squared minus 4.
Volume with the radius r small, this r small, right? Minus volume of this here with radius a. So every time we need to subtract the whole because the whole is empty. Okay, we will include that charge later, but for now, without the charge. So it's a volume with the radius r small minus volume with the radius a. Okay, and since charge of distribution is uniform, so this row and this row, they are the same because we have uniform distribution of charge. I didn't write it down, but I tacitly assume. It doesn't matter which charge you use, charge density will be the same. Right, so I can write, so now I can combine them, so it will be Q over this equals to Q prime over VR minus VA. So this is given. We can write this in terms of formulas, so we can solve it for Q prime. Essentially, that's what I did.
Shouldn't,
Did I do something wrong?
we're solving for charge density.
No, we're solving not for charge density. We're solving for this amount of charge which in this part of the object. This you see, bluish.
Yes.
So that's our unknown, Q prime.
Oh, okay, sorry. Different approach.
So I was going to say it's like the left side is the smaller one, and the right side.
What do you mean left side? This?
Yeah.
No, this is the, we're using the whole, this charged
Oh,
object.
okay.
And this, we used only this part of the object. Yeah. So from here, you know what, let me do this, write it in this part. So it will be Q prime equals to Q and ratio of those differences. So it's a VR minus VA divided by VB minus VA every time we subtract holes. So volume is, you remember, it's a 4 pi over 3 R to the power of 3. So that's the definition. So if you plug it, 4 pi over 3 will be cancelled, right? Because it will be upstairs and downstairs. So it will be Q, and the ratio of R3 minus A to the power of 3 divided by B cubed minus A cubed. So that's, but again, it's only part of the charge. Now we need to, you see, this charge Q small is also inside. So we need to take this plus this, and that's our Q enclosed total charge, which is physically present. So this is our Gaussian surface, and we see this bluish plus this charge at the center. Physically, everything which is inside. You see, guys? And quite often, I give a problem like this, and the students start imagining something, try to find charge density of this charge. No, it's just a point charge Q, just what we've done, what you did in your homework, and now plus just Q small. Yeah.
Would it still be equivalent, like credit-wise on the exam, if we say, okay, we know that there's some total amount of charge distributed in the volume, right? So then we just solve for charge density because we're given the radiuses. And then we say that the total charge enclosed in this smaller sphere is just the charge density times the volume of the smaller sphere.
I used to do it for many years, and still, since we're getting like 30% of students who can still find the correct amount. So a few years ago, I switched to this way of explaining. First, write this definition and then apply this and that. That's my first original approach. But since it didn't work somewhat as I expected, so I thought, I tried once in the office explaining to one of the students, and he said, wow, I like this way of explanation. So I started switching to this approach. But yeah, I used to do it, what you just said. Yeah. Absolutely correct. I just tried to find what works better, right? So based on my experience, and lately I clicked to this. Yeah. Okay, so now I need to get more space. Right. And we're almost done with this problem. Okay, at least the hard part. So now I can write that Q enclosed, it will be Q small plus what we just derived. No, it's definitely, I need to change marker. Right. Alternative, for example, I can do, what if I, instead of point charge, I introduce another small sphere inside with a total amount of charge Q? Would it change anything in, it would be exactly the same. It will be exactly the same because that sphere will be totally inside and just a total amount of charge inside of that sphere, which can be Q small, so it will give us exactly the same formula. Okay, you know what, let me change marker because it's getting too, losing contrast.
Okay, so now let's just plug it into what we introduced. So, oh, it's nice. Back. So E times 4 pi r squared. You know what? Let me first write in terms of Q enclosed. So E will be equal to. Over here, I have to. Yeah, let me start. So that's Q enclosed, and now divided by 4 pi epsilon naught and r to the power of 2. Kind of messy, but again, ideologically, similar to what you had in your homework. In your homework, we had a problem without discharge at the center. So essentially, it's like exactly what your homework, but you just over here need to add this Q small. So that's the electric field. Let me frame it. And of course, it's a 4R between A and B. Yeah. Okay, now, without going through all this, what if I ask, for example, find the electric field outside? So this will be. Oh, I'm getting better in English. Up to this point, it will be again exactly the same. Now Q enclosed. What will be the Q enclosed if we want to find the electric field outside and the Gaussian surface will be here outside? What will be the total amount of charge? Q enclosed. What will be Q enclosed? Q. Yeah. Q small plus Q capital. So it's a banal situation, right? And I think in the previous few years, I had something like this, but still students, since sometimes lack of a little bit of understanding, and they still try to write something like this crazy. No. If it's over here, when part of this charge is involved, yeah, you have to go through, you have to jump through all these loops, right? Hoops. But if it's outside, just Q small plus Q capital, they're all inside, right? Or what if you want to find the electric field over here? Then what will be Q enclosed? Just Q small. Right? So those are banal situations. But of course, I picked on purpose the most complicated, just to refresh. Yeah.
So would it matter if like Q had like a arbitrary length that was like going, say it was like 5 centimeters away from the center?
Oh, don't do that. That's we will never look at that because it ruins the symmetry and all these arguments. It's a joke.
Okay, so never worry.
It's the Gauss's law. It works as well as this when you have a nice symmetrical distribution of charges. Spherical, cylindrical, planar symmetry, great. But once you ruin the symmetry, it will be nasty. So, gradient level EMAG course, maybe at some point. It's probably one of the most complicated courses when you know physics, but sometimes getting through calculus. No, only symmetrical situation. We will never know. Yeah.
No, the calc too, don't. Yeah.
No, the thing is, even if you go to a graduate level course, let's say electricity and magnetism, they still discuss the same physics. Just the level of systems, complexity of the systems much more complicated. Systems are much more complicated. But still, the same Gauss's law, all this Faraday's law in the future, right? So physics is the same. It's sort of like I usually compare with the helical motion. So here there's a material, and you just first you're flying over the material at the low level. Then you go higher, or still over the same physics, but now complexity is more complicated. And then, still the same physics, but level of complexity higher. All right. So enough. Okay. So enough of this. This. Now let's the rest of the exam review session. Let's just play with the recent material which we just started. Which we finished always discussing. Yeah. Okay, I will probably. So this problem I will be able to fit over here. So that's our
Okay, according to my notes, it should be 6. I think I miscounted. So it should be problem 7. I saw this problem in the exam of another instructor, and I thought, oh, yeah, I can include it into my exam review session, just to add some fresh problems. And somewhat similar we will discuss on Monday in our class, because one problem left unsolved from today's class, so I will discuss it on Monday. So let's assume that we have 2 point charges. 2 point charges. Values are given. Let's say Q1 equals to 1 microcoulomb 10 to the power of -6. Table with prefixes again in the formula sheet will be given, so you can look nano, pico, no pico, right? Femto. All right. So Q2 equals to -2 microcoulombs. Okay, so and there are 2 situations. Okay, 2 initial situation. 2 point charges half a meter away, and we're holding them. So they're not moving. So this charge and that charge half a meter away. Then I will do some work, and I will pull them apart and increase the distance to 1 meter. Still the same charges, I'm still holding it. And now the question, how much of work do I have to do? How much of my breakfast do I have to spend to pull them apart? Because these charges, you see, positive and negative, they will try to, they attract each other. They want to move toward each other, but I'm holding them, and of course, in order to pull them apart, I need to do some work. So let's calculate how much of work we have to do to pull them apart, to move from half a meter to 1 meter. Right, so let me draw the situation. Initial situation, I. So let's say this is my Q1. This is my Q2. Our Q2. The ownership. Distance L. L is 0.5 meters. Let me write L equals to 0.5 meters. Then, final situation. I can use my force, I will pull them apart. So let's say Q1 is still at the same place, and Q2 will be moved over here. So Q2, so that's the final situation. So now the distance is 2L. So we need to calculate how much of work. Work done, let's say by me, to move them. Of course, from initial position to the final. Okay, from the initial configuration to the final configuration. First, it sounds like, oh my God, what do we have to do? All right. Okay, let me draw the line, and you can start thinking, processing, and meanwhile, I will exercise. You know, sometimes after the exam review session, I feel like I need some physical therapy, right? Because really, you keep writing, keep erasing for several hours. After that, my arm sometimes hurts. All right. Okay. Where did we see work? So I'm just trying to estimate what are the options, our options of finding the work. First, okay, let me write our options of finding. Yeah, okay, I hear the first option. Basically, what you said, it's a definition of work. That's how work is defined. That's how we introduce it in every class. That's how I did, for example, like just recently in classical mechanics. So it's a integral of F dot dr. You integrate force over between the initial and the final point. So basically, by definition, direct way of finding the work. So it's one option. So let me write one. Direct way
using definition. Using definition. So which is work equals to the integral, okay, from the initial to the final, f dot dr. And you know what? It's doable. It's just a Coulomb's law. It's not undoable, and I think I did it in classical mechanics, proving that no, that was done for the gravitational force, but the difference between gravitational and Coulomb's, they're basically identical philosophically. So yeah, it can be done, but it's more tedious, more time consuming. So again, it's possible, but I prefer not to do this. Right? Possible, but let me write tedious. Wait. Fix it. And again, I put a set way. So I don't want to go this way. Let me write. I don't want. I'm picky. So, but anything else? Second method.
Change in energy.
Yeah.
Something like that.
So we already used a few times during the derivation, but not in the problems. I was planning to use it on Monday, right, in the problem. So the second method, I call it indirect. Direct method. Basically, by evaluating some other quantities, I can get information about what I want to find, about the work, right? So indirect method. W equals to the negative change in the potential energy. Do you remember in physics 1 you used it, and in this semester we used it in the derivations, but not in the problems, not yet, because again, as I said, I'm planning to do it on Monday, right? And so, 2-point charges, finding electric potential energy between 2-point charges, it's a piece of cake. Here, 2-point charges are given, distance as well given, that's it. So it turns out it's a one-star problem, essentially, in the book's notations, right? But again, if you do this way, again, it's possible. But you will do some. You will have to do. You will have to sweat. You will have to sweat all of it. Right. Okay. So yeah, I like it. I like this. And so potential energy, 2-point charges. It's a Q1 times Q2 over R. In this case, of course, never use absolute value because now potential energies can be positive, can be negative. It's not the magnitude of the vector. It's a scalar function which can be positive, can be negative, right? So never try to drop pluses or drop minuses. Okay, so now we just need to write W equals minus U. Whenever you see W, whenever you see delta, it's a final value minus initial, never flip, right? Every time, final minus initial, by definition. So it's a U final minus U initial. And we have minus in front. So let's just open it up. So it's a U initial minus U final. U initial minus U final. And we have a formula. Okay, let me frame it because essentially it's not the definition, it's just a formula for this particular system, potential energy of this particular system. All right, okay, I can write it. It's K, the charges are different here. So Q1, Q2 divided by initial, it's a L, right? And then minus K, Q1, Q2 divided by 2L. Don't start immediately plugging numbers, right? So first simplify it and then only start plugging numbers. So essentially I can multiply it by 2 divided by 2. As a result, it will be okay, Q1, Q2 divided by 2L. You see, right? Will be K Q1 Q2 divided by 2L. Okay, I subtracted 2 similar terms. You see? Here we didn't have this 2, so here it's divided by L by smaller value.
and here divided by 2L. It's a larger value. So it means that this function I can bring to the common denominator by multiplying by 2 and by 2 upstairs and downstairs. You remember? Now we see common denominator. So it's a 2L goes here, and then we have 2 minus 1. We have 1. Okay, and only now you can plug numbers. And L is a half a meter, it's a 0.2 meters. So downstairs it will be just 1. Okay, I'm not going to plug numbers. You know what? Anyway, so the value, will it be positive or negative? Negative, because one of the charges is negative, so don't drop that minus. I will write immediately the answer. So it's a minus 18 times 10 to the power of minus 3. Units of work, do you remember physics 1? Yeah, joules, yeah. Units of work, units of energy, joules. That's it. First, it sounds like, wow, complicated something, but once you start thinking, it's not that bad.
Will the constants like K and epsilon naught be on like the sheet?
Yes, of course. Those universal constants, no, I don't expect you to remember them. But of course, if you use them on the almost everyday basis, of course, you will start remembering just nature of the things. But of course, those constants are good. Although when we were students, when I was a student, we had to remember everything. But that was a different system, and they were much more brutal to us in terms of demanding. No formulas, no constants. Remember everything. Or derive. If you don't remember, take your 10 minutes and derive everything. All right. Yeah, this problem will be on Monday. Something similar, but instead of, for example, charges, I think the potential will be given. Okay, the last two problems, but they are somewhat lengthy. Somewhat. You remember charges with moving charges in the in the capacitor, and we applied two methods: energy approach, force approach. Now let's do similar, and then 2-point charges again: energy approach and force approach. And after that, I think it will be should be enough. I think I should be able to fit it here. Let me get separated. And so this should be problem number 8. Yeah, let's first solve this problem, and the second it will be somewhat faster. The last one. So there is a capacitor, and they call it plate A and B. Okay, let me start with the picture. It will be easier for me to explain. So positively charged plate and negatively charged plate. Let me position it here. Right, minus, 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 and plus, 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 plus. Usually on all my pictures, which we used in the class, every time negatively charged plate was here, but now I just flipped, and it was given in the problem. Well, just so that you get used to different configuration. So it's called plate A and plate B. Right. So of course there is an electric field. What's the direction of the electric field? Electric field lines. From plus to minus. Yeah. So they will be this way. So these are electric field lines. Okay, almost parallel to each other. You know, it annoys me. Yeah, this is better. And the value of the electric field is given. So electric field is 12,000 newtons per coulombs. Electric field is given. Then we take what is electron. So then electron is shot. From which point? From plate A. So over here, it's an electron which is shot that way. with initial velocity v naught.
Should the electron come from the negative?
Yeah, we're shooting it. So we are forcing it to move in the direction in which it doesn't want to go, right? Because you remember, of course, it will be repelled by that plate, but since we shoot it, of course, it will fly. We are forcing brutally. All right, so initial velocity is given, oh, it's quite a large number. It's like what? 1,000 kilometers per second. Right?
Just like orbital speed.
Yeah. Right. So with this velocity, and we claim that it is going to, of course, first of all, it's going to decelerate, right? And so it will fly for some time, for some distance. Of course, then it will most likely stop. Right? Okay, numbers are picked in such a way that it will stop before colliding with the negative plate. And turns around, and of course, it will fly in the opposite direction. So, distance between plates is given. D, 40 millimeters, yeah. So, distance between plates is given. And so we need to find the distance between the negative electrode and the turning point. So we need to find this distance. Let me show it with blue. So we need to find that distance. Okay, why I didn't write in terms of symbols? Because I need to introduce coordinate system, and then it will be kind of nicer. Yes. Okay, now, one of the most important part in this problem. Where should we position the origin of our coordinate system? Of course, you can position it anywhere you want, but usually we measure distance to the charge in our formulas from which plate? When we derive this formula, these and these, do you remember? Actually, it's here. You see, the reference point and the origin, we usually position the negative electron. My recommendation is the same. Although if you measure it from the plus, you will have to be more careful, right? So usually try to follow the derivations. Okay, so it means that our x-axis will be pointing in this unusual to the left. And this will be our x equals 0. Of course, over here it will be x initial. What's the value of x initial? We shoot it from this electrode. So x initial is what? Okay, let's use symbols. We're going to plug numbers later. D. Yes, D. This is the place where students start making some mistakes because now we flip the system around, right? So now initial point is not 0. Usually we shoot objects from 0, but now we shoot it from D. And the final, actually we need to find. So let me call this x final, and that's essentially we need to find. If we find that x final, it's a distance from the negative electron. So we just need to find x final. Okay, I think now we have everything which we need on the picture, except for, we also can say about the final velocity something. 0. It's a turning point, right? It's a turning point, so over here I can write, so v final equals to 0. I think now picture is complete. Gorgeous. All right. And I'm still checking. Yeah, let's give it. Yeah. So, and I'm going to use again two methods. First method, actually it's a second method since we introduced it just recently. So energy approach and then force approach. On the exam, if a problem doesn't say which method should be used, you're free to use any method you want, right? Even invent your own, so as long as it works, right? But if a problem says use energy approach or force approach, of course, I'm going to check that particular method. If you try to use different method, I have a reason to subtract at least 50%. Right? So in the graduate level course, I remember one student tried to pull that. I didn't understand. No, I couldn't. So use the method which we're asking. Yeah, so okay, energy approach. Since there are no any losses, force, electric force is a conservative force, we can introduce potential energy, so the total mechanical energy stays constant. So I can write, so E initial equals to the total mechanical energy at the final moment. So this is the initial position, this is the final configuration. So, so now let's start diving. So it's a K initial plus U initial equals to K final plus U final. Whew. Now, kinetic energy final is 0, right? 0. We can reach this. Right. And potential energy. Do we have the expression for the potential energy of a point charge exposed to a uniform electric field, in this case created by a capacitor? It's the formula which I derived in the class. You see? This is the wrong system. Don't even think about using this, right? So, but although sometimes students try to use this one. Q, E, and X is the distance from the negative electrode, and we did that way. We introduced coordinates, right? So, or you can do it in step by step. So first, write U equals QV, and then V equals EX. It's just basically you splitting that one step with two steps. Potato, potato. So U equals to Q, E, and I will use X. So again, I derived that formula in the class. Okay, so now let's just write down and see what we're going to get. Initial 1/2 mv initial squared plus Q E X initial equals to Q E X final. How many unknowns? X final. The rest is given. So one unknown, one equation. Physics is done. So physics is over. Now it's just we need to solve it for what do we need to solve? This is X final. So this is our question. So I need to divide the whole equation by QE. Each term by QE in order to make my unknown free of any constant factor. Right? So, and then of course I will flip it, so X final will be in front. So it will be X initial because QE and this QE will be cancelled. Right? So you see it's X initial plus MV initial squared over 2 Q times E. Okay, now let me ask you. It looks like we have X initial, you see in the formula, and plus some additional term. Does it mean that our final point somewhere will be on this outside of the capacitor? Why not? Why isn't it going to be outside of the capacitor? Look at the formula which we derived. MV2QE. So what can you say about
Q is negative?
Yeah, Q is negative, so this term will be negative. So we're going to actually subtract some value from the initial value, right? So it will be X initial D minus something, yeah, so we're going to be within the capacitor. Right? So it makes sense. Right, so yeah, it's going to be negative. Okay, I'm not going to plug numbers. Right. So again, mass of the electron, I definitely remember it was 911 times 10 to the power, I think, minus 31, right? So, yeah. And again, those numbers will be given. Charge of an electron, everyone usually remembers, right? But of course, it's still given in the formula sheet. So, it will be, okay, X initial, of course, it's a 40 millimeters. And if you convert this term into millimeters, you will get minus 23.7 millimeters. Of course, first you need to use meters and everything, but then at the end, you convert. So it will be equal, if you subtract, 16.3 millimeters. 16.3 millimeters. So energy approach. It's similar to what we did in a class, but in a class I think we were shooting till the very end, till the negative electrode or positive, I don't remember what. Now it's somewhere in the middle. We're stopping it. So now let's do it quickly using the force approach. Good? Yeah. And again, based on my experience, most of the students do reasonably well if they put some effort, if it's some effort in learning. Essentially, it's a physics one, except for the nature of the potential energy. It's an electrical potential energy, not gravitational, but ideology exactly the same. So it's not new, right? And now the first approach, the force one. So, and again, we use this method at the very beginning of the semester, which is, of course, you need to first write down the expression for the force, in this case electric force, then mix it with Newton's second law equation of motion, get acceleration, check if acceleration constant, grab one of the kinetic equations, and apply. So standard procedure, which we've done many times, and I even created the skeleton for you, I remember at some point of these problems, but I don't want to do it now. Okay, so force, F. And of course, the formula which we used at the very beginning for the electric force, right? So it's a Q times E. Right? It's that one. Q times E. So Q times E, and I want to write it in a vector form because, yeah, we're dealing with the vector quantities, and sometimes we need to show explicitly minuses which we need to use, especially in acceleration. So, charge is negative. Let me show that negativity immediately from the very beginning. Electron, so I show that minus from the very beginning. Then, electric field. What's the direction of the electric field? Is it positive or negative as a vector, one-dimensional vector? Electric field. It's a one-dimensional vector, so I can say is it positive or is it negative? Positive, it means it's in the direction of the positive x-axis. Negative, it's in the direction opposite. So our electric field is, look at the x-axis, and at the picture, and you look at the direction of the electric field. X-axis, you see, I pointed this way, to your left. You see, but the electric field is that way. So every time look relative to the coordinate system you introduced. Right? So I can write that it's a minus E and in the x hat direction. Negative x hat direction. So it means that force will be positive, and it makes sense. Positive force, it's in a positive x direction. So yeah, this electron will be attracted by the positive plate and repelled by the negative plate, which means that positive x direction. So you see mathematics explains. So I can write absolute value of Q times E and in positive x direction. So that's, we wrote explicitly the expression for the force. Yeah.
So x hat means positive.
Yeah, positive x, it's a unit vector showing positive x direction. It's a very convenient unit vectors, which I use almost everywhere. Sometimes I hat, j hat, k. I think that's what we usually use in this course. I hat, j hat. Okay, x hat is also used very often. So, and now we need to mix it with Newton's second law, or not mix, use it in the Newton's second law, equation of motion. So from here we'll get acceleration as a vector. So it will be F over M. So it will be Q times E over M, and acceleration in the positive x direction. So velocity that way, acceleration positive, but actually it's a deceleration. So you see positive acceleration, but it's a deceleration. Positive and negative, it means just what's the direction of the acceleration of a vector relative to your positive x-axis, the direction of x-axis. But in this case, velocity this way, but acceleration this way, deceleration, although it's possible. In physics 1, we usually discuss that also. Okay, so constant acceleration. Yeah, it's constant. You see, it's constant, so it means that we can use kinematic equations. So, kinematic equations can be used. Right, which is good. Right. Which kinematic equation to use? Of course, there are different ways. Just there is a more efficient, less efficient approach. Which equation will be the best? My test is usually, do we have information about time?
So
Is the question about time?
no. So
It's a clear indication that equation number 3 will be the most convenient, right? So it's not about time. We derive the equation for these special situations where we don't care about time. So it's, yeah. Is that v squared equals v naught squared? Yeah. V squared equals to v naught squared plus 2a x final minus x initial. What? Revelation.
But we're given that on the exam.
Yes, of course, kinematic equations, of course, given. They will be given us because we use them very, very often. Because we don't want to deal with second order differential equation now because you're not at that level. Right? So right now you're still learning integration. Right? Although it should be already behind your belt, right? So at this point. Final velocity is 0. It's a turning point, right? So this is our final point. So it's 0. We can simplify it immediately. X initial and x final, are they 0?
No.
Nothing is 0. So we need to drag that throughout everything. And our question, of course, final. Yeah, that's our question. All right. So let me do it step by step. So it will be 2a x final minus x initial equals to minus v naught squared. I just move v naught squared to the other side of the equation with minus. And now divided by 2a and move x initial to that point. Okay, I will skip one step. I'm sure that you can follow me. Minus, yeah, good. V naught squared over 2 times a. Okay, so now let's insert acceleration over here, right? So as a result, we will get x initial minus v naught squared over 2, and acceleration is q e over m. You know what, let me move m immediately upstairs in the numerator. You see, it's right now this divided by that, it means m must be upstairs here. So, are we getting the same? Like in the first method? Yeah, here it's only minus, it's just minus appeared because I showed that electron is negative from the very beginning. But here I kept it hidden for the discussion at the end, so here it's negative. So exactly the same. And in this case, both approaches are trivial. Both approaches are easy. So the same, great. Right, wait. The same, and of course happy face. Right, so of course answer will be the same. Okay, and the last problem, which is easier. All right, so this problem. Okay, any questions so far? I think yeah, we discussed it thoroughly. I think I need to erase this hat. So essentially, what right now we practice essentially this formula: the system when we have a parallel interaction of a point charge with a parallel plate capacitor. Uniform electric field created by a PP capacitor. Now 2 point charges. So that's the last one, and we'll call it. So that was number 8, now number 9. So, okay, physical situation. Let's say assume that somebody shot an electron would, no, proton from infinity. You wanted to go to infinity, and so shot an electron from a proton from infinity. And let's say we want to stop it. Let's say something is important over here, so we don't want to damage it with that proton, right? So we want to just decide how much of charge we have to put over here in order to stop that proton, let's say at a certain distance away. So the proton flies with gigantic velocity, and we want to stop it with the electric field. We position here some point charge, and we want to find how much of charge we have to put here so that the proton would stop at a certain distance r from this charge. Something like this. Okay, let me draw the picture. And first I will just write 2-point charges system. 2-point charges. Even this marker is losing contrast, but I will be able to finish it. So 2-point charges. One is proton. Q, it's a proton. Small. Okay, let me draw now the situation. So this is our proton plus weight. Q, which is short, as I said, with velocity, initial velocity. Again, 1,000 kilometers per second. It's like in the previous problem. Of course, it will fly this way. And as I said, we want to stop it. So over here, and the distance r equals to infinity. So this initial velocity is at infinity. And so I want here to position Q capital, which we want to find how much of charge, so that this proton would stop over here, turns around, and moves away. So we want to find this amount of charge, so that this distance, so the proton would stop at the distance r. Of course, this is a stationary charge. Maybe it wants to fly away, but we want to stop the proton, so we hold it. So stationary. It wants to go, but we're not allowing stationary. And of course, it can be done. So, no numbers, essentially. So everything will be solved in using symbols. Okay, and let me write the question. So we need to find Q so that the proton stops. Okay, turning point. Turning point. Of course, I'm talking about turning point. Electron stops at distance r from Q capital. Some imaginary situation. Again, ideologically, it's very similar to the problem which we solved in the class. I just decided to find different things and change. Instead of 2 electrons, now it's a proton and some charge. But ideologically, it's a similar problem. And I think so again, 2 approaches, like over here. Let's first try energy approach since it's a new, and then again we will try the force approach. So approach number 2, energy. Again, electric force is a conservative. We can introduce potential energy. There are no any losses. It's vacuum, so no interactions of the proton with any molecules or whatever. So it's just a vacuum. So I can write that E initial equals to E final. Initial, it's this point, and final when the proton is at the turning point. Right? So, and again, like over there, but now of course it's a different system. It's not a point charge inside of a uniform electric field, it's a 2-point charge, so we need to use the correct formula for that. And so again, I will write K initial plus U initial equals to K final plus U final. Diving until we'll start seeing all our quantities which are given and which needs to be found. Okay, let's start. No, you know what? First, let's pick the right formula for the potential energy. Which is the correct formula for the potential energy for this system? Potential energy, energy of interaction.
K. Big Q, small q, R.
Yeah.
This one.
Not squared.
Not squared. Yes, sometimes. After using this formula a lot, sometimes it's just a force of habit. You keep writing R squared.
Yes, that person is me.
All right. So U equals K. Q small, Q capital over R. R is the distance between, right? And so again, this is the essentially not definition, it's the formula which we derive. So let's write U initial. What can you say about initial potential energy? Yeah. Because R is, what's the value of R?
Real big.
Yeah. K, Q, Q, and R, which is at infinity, R initial. It's 0. Right? So it's 0. It's nice, right? So when something goes to 0, so U initial, it's this is 0. Yeah. Then, final kinetic energy. It's a turning point. It's a turning point. Right, good. K final, 0, since V final is 0, it's a turning point. V final equals 0. And let's write also, no, immediately I will write in the formula. So this is also 0, so we have only 2 terms. Kinetic energy, initial kinetic energy will be converted completely into the potential energy of the system. So it's just conversion of one energy into the other one. So it's probably one of the easiest problems. Right? So now I can write explicitly. So it's 1 over 2 mv initial squared, or I use not. Okay, let me use 0. This 0 and then equals to k q small q capital and divided by which distance?
R.
R capital. Now it's R capital because that's our final point, turning point. We want to achieve at that distance, so we put it here. And you usually answer the questions, how many unknowns in the equation?
Just one.
Just again, our Q capital. One equation, one unknown. Again, physics is over now. We just need to solve it for that. Q capital. Nothing can be cancelled, so we just need to solve it for Q. That's it. So Q equals R goes here, so it will be mv naught squared times R, and divided by KQ, Q small. Yeah, Q small. That's it. So no numbers, and sometimes I do give a problems like this. Of course, I know sometimes students have really dependence. I remember many years ago there was one student, and he would ask, "Just give me the numbers at the very end," like an addiction. And of course, it's not very good. You need to also develop a habit of working with just symbols. Right? So something is not clear.
Did you get rid of the 1/2?
You know what? It's possible. Yeah, I'm still human. Plus, it's a Friday evening. Yes, absolutely. So it goes next to 2, next to KQ. Yeah, thank you. I'm still human. Right? The second approach. Just collapse. Great? Yeah. Good? Okay. Okay, maybe not great. All right, and of course the first approach. Again, what will be the problem with the force approach in this study?
Just realized K constant for good.
Yeah, it's that sometimes it's called the Coulomb's constant, but usually called just 8. It's that 8.99 or just 9.0 times 10 to the power of 9
power.
newtons times meter squared divided by Coulomb squared. But of course, that is given in the formula. So, what will be the problem with the force approach?
Force with respect to distance is not constant.
And the same acceleration will be not constant. And of course, again, it's not the end of the world, right? So you can still can solve the problem by solving second order differential equation, but of course it's much more complicated. So, okay, but let me come back. So in this case,
the entire test.
F equals K Q small Q capital over R squared. Now it's a Coulomb's law. Right now we're using the force approach. Now we need to mix it with the Newton's second law. So acceleration will be F over M. So it will be K Q capital over M R squared. And because of this R squared, it ruins the game. So as a result, it's not constant, and as a result, kinematic equations cannot be used. So kinematic equations cannot be used. Again, it can be solved, but again, it will be much more complicated. So it will lead to the differential equation dE, and it's much more complicated. Much more complicated. Yeah. And of course, we're not discussing it. It's sort of outside of the scope of this course. And of course, if I give a problem like this, you have to use the energy approach. Right? Oh, go through that, but properly.
So would you probably tell us in advance? Or
Yes,
do you think
yes.
probably-
You know what? For this type of problems, I don't tell usually which approach, because it's sort of kind of obvious. But I will. Yeah.
I was gonna say, it's like at that point, it seems like the energy approach is always the safe bet.
Again, as I told you in the class, the advantages and disadvantages about energy and force approach. Energy approach allows you to find a certain value, a certain quantity at a certain point faster and easier. But you're losing the history. What happens with the system between initial and that final point? So all the history is lost, right? Because of that integration when you introduce this energy approach. But if you use force approach using Newton's second law, you're pretty much getting a function. So you plug the time and it will tell you what happens to the system at that particular moment of time, or this moment of time, or that moment of time. But the energy approach is just on the initial and the final point. It's sort of like as I compare it with the trip to, let's say, LA. There are two ways. You can either buy a plane ticket, just fly there quickly without seeing anything, right? So faster, more convenient, right? Easier, but you don't see the flowers and trees. But if you drive, you see everything. Plane ticket for driving versus driving. That's again the major difference between the approaches. Okay, so that's what I prepared. 8 problems, and what's the story? Yeah, 2 hours. Oh no, 2.5 hours. Yeah, that's usually the range of the exam review session for exam 1 and exam 2. Of course, this semester we're not going to have problems on the exam about conversion between connections between the electric field and the electric potential, which is usually in the past it was on the first midterm exam. We are behind my schedule by 1 class. Because again, we're using this format for the first time, and as a result, okay, if you have any additional questions, ask. And but if not, then I will hope everything works.